Okay, here we go. So the last thing we're going to do this semester, I wanted to do maybe one more, but we're still about 3 days ahead last year, so. And we finished plenty of time last year, so we'll be good. Okay, so 4.4 is the fundamental theorem of calculus. Fundamental theorem of calculus is very, very deep. If you understand it fully, then you understand all of calculus. All single variable calculus anyway. So like the last class, one of the last classes I took, a lot of it was study of the fundamental theorem in much greater depth than we would do in here. There's two parts. Part A is what we'll do this week. Okay? Part A is very easy. Actually, both parts aren't that hard. They're not hard to use. To really understand them takes a bit more. But we'll do the fundamental theorem, part 1. Fundamental theorem of calc. It's crazy that you can understand like everything with just this one theorem. That's 2 parts. So part 1. Of course, just like those other theorems we've studied, and this is like, what do you think? I think this is the last theorem of the year. This is the last one. We've seen them all. So what are the theorems we've learned this year so far? There's only like 4 or 5 that are ever on the AP exam.
The mean value theorem.
Mean value, which we did very well on. Rolle's theorem, which is kind of mean value. This, it's 3.
Something to
Intermediate value theorem. And extreme value theorem, which we barely just touched on because they're so simple. So, that's it.
The names.
I don't remember those at all.
Well, of course, we'll go back and review them. So it's not a very theorem-oriented class, really, right? So if f is continuous, they all had hypotheses, right? So the function f has to be continuous on a closed interval. A to B. It's like the same thing that was true for some of those other ones, right? Not very hard. And you've also got to know capital F. What was capital F usually? Yeah, it's like the antiderivative. Very good. I used to always have trouble with that. And capital F is the antiderivative of f, little f. Then we know 2 things, only one of which we'll see today. But the first thing says that the definite integral on that interval, that interval, the integral over that of little f dx equals the antiderivative at the end. So you evaluate it at the end, and then you evaluate it at the beginning, and you subtract. So why does this work and stuff? What's the proof? I think that those questions would take us
What's
quite a
the
bit
purpose
of
of
other
finding
stuff to learn. But what's it say is something so simple. This tells you how to evaluate these kinds of integrals. Before, how are we doing them so far? We only had 2 ways to do them.
calculator.
We can use the calculator, which what's the calculator do? Remember, it uses the rectangles, and it uses a very, very small width, or
We could find the area.
like geometrically, but for instance, for a parabola, you guys know a geometric formula for under x squared? So even that, like one of the simplest examples, we were like, I'm stuck. This tells you how to do it. So luckily using this is pretty easy. So let's just do some examples. That's all we're going to do today. Do like 4 of these, and like, you're good. Oh, then I have to tell you one other thing. I guess it's like a corollary. Oh, it's
Nice. It's got every day actually.
I won't do it.
So it's kind of like we're going to do those same integrals we did before, except now we're actually doing definite ones that have some numerical answer. Yep. And if you're ever on the AP exam and you're presented with this, would you do it by hand? No. What would you do?
Calculator.
And use
The
That thing
infinite.
that you-
Math
Yeah.
9, exactly. If we ever on the calculator portion of that exam, we're going to go Math 9.
It's big.
Yeah. Well, I mean, these are pretty fast too, but you're not even going to worry about wasting time. We'll get to that. Let's do those two. So I'll do these two with you guys, and then I'll maybe give you one to practice on your own.
Where's that?
Okay. Equals what? So first you've got to figure out the antiderivative, right? So there's some notation that kind of goes along with this that's slightly new. So I'm going to say this equals, the integral equals, you can write it right there if you want, I'm not going to save space.
You plug in 1 and then 3.
I need the antiderivative first though, so let's just do the antiderivative. Ignore. What's this? 3x
Over.
Over
cubed
So
over
it'd just
3.
be x. Yeah.
And then here,
5x squared over
5
2
halves.
minus 4x.
do we need plus c?
Yeah. It's not for this. Because you're
No,
plugging
because
in.
now we've specified from that whole family of possible solutions, we want the one that is the area between 1 and 3. So what you're going to do is you're going to write, I think usually these are brackets, I'm going to do it like that. So bracket, and you put a 1, a 3. Sometimes they use a vertical bar. I'm not going to be real picky, they don't care either. So. Okay, so that means evaluate this guy. So remember the vertical bar meant to evaluate at those two things. So then you plug in. So you plug in 3. So we get 3 cubed plus 5 halves times 3 squared minus 4 times 3. Notice you want some big parentheses around the edges. Be careful, because
Because
the
it's
way you
not-
mess up here is you don't distribute or something. That's deadly. Minus, now you plug 1 in. Sometimes it's just nice to actually do the calculations to shortcut it for yourself. What's 1 cubed? 1. What's 1
5
squared?
halves.
So that's going to be 5 halves minus 4. See, so I kind of like to do it like that. Be careful though. And then equals whatever, you just keep simplifying it down. So take a little bit of time, it's 27. 9 times 5 is,
45
you have your calculator though, so minus negative 3 plus 2.5. See, I'm starting to think about these decimal fractions. I'm doing whatever's easiest. So I'm going negative 3 plus 2.5 is negative 0.5. I'm starting to think like that. So then I've got 27 minus 12 is 15 plus 45 over 2 plus 1/2. That's going to be 30 over 2 plus 46 over 2 plus 76 over 2. That goes in. 30,
Is that 46 over 2?
what is it? 30,
38.
38? Thank you. So, in essence, the integral is, if you put it in your calculator, it's going to tell you 38. So can you check these with your calculator, Kevin? I welcome you to do that. You need to know how to do both ways. Okay, this one. How do I do that one?
I pull it apart first.
Break it
4
apart.
equal
Yeah. So we'll go 4, what's that over that?
1.
1. They like cancel totally, right? And then what's that over that? Isn't it that? 1 over root x is x to the negative 1/2. You can write out another step if you want. I think you guys are mainly ready for that though. So leave your 4 out in front. And antiderivative of 1 is
X.
x. Antiderivative of this is x to the 1/2 over 1/2 is 2. Evaluate from 0 to 3. Questions so far? Okay.
Yeah, so you able to pull that out like that, the 4 from the whole thing?
Are you able to pull a 4 outside of an
You
integral?
have a plus, the way you pulled it out, because you have 4 root x over,
Is that legal? I was thinking it was.
no,
Look at it again.
yeah,
This should really be...
4x.
Now you can pull this out if it was 4 here too, but it's
Yeah.
got 2 terms, huh? I better be careful. And leave that 4 right there, which means that 4 goes right there. Thank you. And then I use the fundamental theorem to say, how do you do that?
Substitute it.
4 times 3 plus, that's back to square root, right? So maybe we better think of that back as a square root to help us out here. Plus 2 root 3 minus, so when I do integrals, I like to sometimes just put like 2 big things in parentheses for the fundamental theorem and put a minus in between right away so I don't forget. I don't have to think hard. So you want to do that, but it's fine.
Oh, yeah.
0, 0 is,
0.
yeah, so 12 plus 2 root 3. Let's see what we get. What is that as a decimal? Remember, your calculator is only approximating these things. It can't hold functions. It can't hold an infinite number of points. It's only doing rectangles of really small width. What'd you get?
15.464.
Give me more decimal places. That's good enough for
10162.
Let's use our calculator and see what it tells us. Can somebody put this in their calculator? Let's go math 9 and see how close it is. I bet it's accurate at least to about there. It might be accurate all the way to that many decimal places. I guarantee it's not going to be accurate once you get down here. You know what I mean? And you might say, well, who cares about that? But if you're flying a jet plane, you care. Because that 5th decimal place could mean life or death.
My calculator. For
Even if you're not flying a jet plane, if you're riding in a plane, you don't want to die.
This is gonna take a bit.
Maybe this calculator.
15.4640.
Did it do it? Same decimal places?
I'm sure there's a way.
Really?
It's
Oh,
still
it's popped up.
calculating.
15 point.
No, it's a different decimal place.
Ha ha ha.
It changes at the 4th decimal.
Does it? So it's
Yeah.
not even that
Yeah.
great, is it?
It's 15.46409.
Yeah. Let's see. Did it take the calculator a second to do it too? Brett's did.
Yeah.
Math 9.
0.
You could put this one in or the original. You could just put the original. Sometimes I like to just do that. So I'm going to go alpha y equals. Oh no.
It's not right there.
Oh no.
Oh.
0 to 3.
Mr. McGee.
Sorry.
I have to say I was a lot more calculator literate when this easy tuber was on the last one.
Helps, huh?
It does. Like for one of them was a really long function and you had to enter multiple things.
It was
So I put
the
in my
same
list and
one.
it was like set entry variables, input stuff in. It's good.
We had the story about the butterflies, the Olympic athlete, and the kit boxes and all that stuff.
Does this look like a boost? I had
Man, this took a second. So I think this problem also illustrates if your like calculator's having trouble crunching one of these down, should you abandon it? Sometimes some of these things we're doing are going to start to take computing time, so don't abandon it. Give it a second. So it's right to the AP's standards. So can you guys see why did AP say 3 decimal places?
Because the calculator.
Because of things exactly like this. 'Cause this is what you're going to be using it for mainly on that test. That's why they say 3 decimal places. So it's off after that, which means I bet if you're that far off, your plane's gonna crash.
Is there any way to get closer?
Yeah,
Use a
we're
smaller
not there.
rectangle size.
Yeah, but
Or
like,
more. Is there a better way to do things? Sure.
yeah.
Depends on how efficient.
So you just make it less than 0 to 3.
Depends on how efficient you are. You could get a better estimate with computers. Sure, but it depends how much computational time you have.
Would that
And it
be-
depends
would it be
how good your
easier
algorithm
to
is.
Use this
So.
theorem right here.
It'd be a lot better to just either do this by hand or somehow program the computer to be able to do this for you, which is hard.
Why come up with a whole new program where you can do it by hand?
That's exactly right. So like I've got to be able to do both. So I think that's a good example. Integrals just like this one. On research that I've done, like big research projects in the past, we've had to like do lots of integrals just like this one that are real simple, and we do those by hand, hard code them into the computer, and then have it do like the big processes after that. So it's, you combine both things, you know. Yeah. Okay, let's try a couple more. How about this? Try a trig one.
Sine and cosine.
You guys, I've noticed as we're in Calc actually, we're probably better at the trig stuff than we are at the basic algebra stuff. Why do you think that is?
Because you made us memorize the units.
Maybe.
I don't remember the unit circle.
Yeah.
It's gone.
This is what happened. It was
But
a
you're
circle
still
and then
able
it
to do
rolled
it
out of my
pretty
mind.
I've noticed you might have to like think for a second on something, but you're still able to pull it out. And you still know when you need to use it.
What if you did it?
What's this?
And I'd be like, I just want to call that a
Is that to be
one.
negative?
It's like a good thing I made insurance.
Positive cotangent.
What's the derivative of cotangent?
Negative.
Negative cosecant squared. So is this, so it's just plain old cotangent of x evaluated at. Okay, you guys practice, evaluate that please.
For 1 second.
Cotangent's one of the ones we don't like to evaluate, so let's see if we do that.
So why did the negative go away?
What's the derivative of regular cotangent?
Is that, yeah. So she's going backwards, okay.
So going backwards, it's not negative, it's the same thing. If this was like this, then you put a negative.
Okay. I guess.
Derivative of cotangent is negative cosecant
Yeah.
squared.
Is it
So if negative cosecant squared is there backwards, is plain old cotangent.
My basic
It's not gonna work with stinky because cosine over sine 0 over.
No.
So you're doing cosine over sine, okay?
It's 3 pi over 4 for the first one.
Oh, over 4.
So
I
it's
was doing-
negative 1.
So notice, you have to be careful. Is it b minus a the same thing as a minus b?
Excuse me.
No.
Gotta do the top thing first, minus.
Oh, okay. I approve of that makes it less popular.
Oh god.
Like, I can't, no, I can't.
For the cotangent, I just did like the tangent and flipped it.
Putting something in
That's great. There's all kinds of ways, Brett. That's great. Exactly.
0.
So if you're having trouble, you might draw this triangle and that. Cosine of this guy is 1 over root 2. Sine is also 1 over root 2. Cosine of pi over 2 is.
Isn't 1
It's 2
negative?
pi over 4 though, so it's gotta be negative
Oh,
1
wrong quadrant.
Your cosine is.
There we go. Yeah. Cosine up here is 0. Sine up here is 1. So you get negative 1 minus 0 equals negative 1. Can you check that with your calculator just like the other ones? Yep. Use radian mode. You know what? I'm going to leave that one off till tomorrow. So let's see. Let's do this. So this is kind of like a sub-theorem. This one's really easy. I'm gonna yeah.
Do you do the same thing if you have like 1 over, like if you're getting like
Can't
values
you?
of, like,
It's not
you do that, you
S.
still write out.
No, it's not. That's never happened to me. I'm like looking at my paper trying to write, and I don't see something. I gotta figure it
Guys,
out.
no. 1 over, she's saying instead of going cosine over sine,
Yeah, but then I was thinking the wrong thing.
you go 1 over tangent. That's what Brett did.
Well, that's what I was asking. So if I did 1 over tangent of 3 pi over 4 minus. Okay.
Yeah, and I mean, if you have your calculator, you can do it that way too. That'd be just as good. Okay, last thing we'll do today. I'll show you one more example tomorrow. It's the average value of a function. Turns out we can just slightly add on one little tiny little thing, and now we can do this crazy thing, which is find the average value of a function anywhere.
What is that though? Like, what is the purpose? Like, why do you want to? What is the average value like?
Good question.
The average value.
Okay, so let's say we have a function that looks like, I don't know, I kind of wanted to draw one that looked like this. Okay, there's function f. What this theorem lets you do, or what this idea lets you do, is let's say you want to look between here and, I don't know, there. Or if you wanted to go between here and here, anywhere. I just picked some interval. It now lets you figure out how high that function is on average. Was there a way to do that before? It sounds like something really simple, right? But if you just had some random crazy curve, was there a way to figure out where the average is? Is it down here? What do you guys think for a to b? Where's the average height of that function? Is it like down toward this dip?
No, it's like
Almost
Up
like
there?
in the middle.
no, like in the middle.
Like directly in the
Sort of in the middle, closer to the
So
bottom.
for
not in the
that
middle of
interval-
X, but like
Yeah, I know what you're saying. How about if I go that a to b?
This.
Now the average value is higher, isn't it? It's going to be like up there more. But how could you figure this thing out before now? I don't think this has ever even been mentioned because it's such a crazy advanced thing. So I'm going to leave it back over here. Yeah, the only way you could have done it is to like guess. So let's trace that up to the curve. So we're thinking the average value is somewhere in the middle. That's what you guys were saying, right? Like maybe right here or
A
something.
little closer to
It's kind of like you have to take this part and kind of offset it with that part in order to find the average value, which is this big red rectangle filled in.
That's the average.
Why am I shading those kinds of things? Can somebody help me figure out what the average value is without me even telling them? Look at the red guy. How do you get that red rectangle?
That would be area.
Would you subtract and then add? I don't know.
It's the area
What's
of
the
rectangle.
area under a curve?
So that is the f of b minus f of a.
Okay. I'm gonna go integral though.
So A to B.
How about the integral of f dx? That would just be like between a and b. The integral of f dx would be like that all underneath there, right? So you wouldn't count this part and you would count that part, correct? How are you gonna fix that issue and just come up with that red square box? You take that integral and do what with it? Anybody got an idea? Just see. You don't have to know this. I just want to see if anyone can come up with it.
You're going to have some point c where at that moment you're also taking the integral above.
You're trying to use like the mean value theorem, kind of. That's good. That's good thinking. Good ideas. It's an average. Think about it. It's like the average.
So add
y
everything
value.
up and divide by.
It's an average.
Oh, candy bar.
You're saying it. Add everything up. Add what everything?
Everybody's.
Add all the area under the curve up. That's what this is. And divide by.
The area of b above the.
Usually you divide by the number of things, right? Divide by what? What's like the equivalent to number of things here?
The change between A and B.
Yeah.
So wait, what was that, Mr. McGee? Like right there, like the f of x dx. What is that in the drawing? Like what does that represent in the drawing? The blue.
Well, it's not in any of those things specifically. That would be like all underneath
All
here,
underneath,
right?
okay.
So it wouldn't include that. It wouldn't include that.
Okay.
What I actually drew in here is red. This is the average value.
Yeah.
Yeah. The idea though is like an average. You take the total area, the total number of things, and you divide by how many things you had, except in this case we're working with continuous stuff, not discrete stuff. And in continuous land, the number of things we had is that chunk of space, which is b minus a long. So I divided by b minus a. You can put b minus a underneath the thing if you want, that's fine too. Okay? So that's the average value, which now allows you to answer crazy questions like this, which before you had no idea. Find the average.
I didn't. He's like, what? I didn't believe you, but then I was thinking, I was like, well, in American Horror Story, your bruises look yellow, so maybe he's telling the truth.
So let's say we have that parabola. We want to find, on average, how high is it between 1 and 4?
So 1 over
All kinds of reasons you might want to know
-3,
that.
the integral of f of x.
So 1 to 4. Put f of x in there. And then when you're all done, divide by,
-1 over -3. Oh,
Divide
4
by-
minus 1. So
divide by 3, essentially, right? You can put it in front, or you can, remember, you can just put divide
So
by 3 if you want. That's fine.
What do you substitute in now? Like from this stuff?
I'm going to give that to you for a second. Look back at that other example.
Do you substitute in both? Like,
Substitute.
like do you do the f of b minus f of a now?
Yeah.
Yeah.
Over.
Find the
Over
antiderivative.
3, okay.
Then plug in. Antiderivative, then plug in, then divide by 3. See what you get.
Did I do this right?
I think the numbers work out pretty nice on this one.
Yes. So then you divide each of those by 3 and then substitute one. Don't talk to me. Talk to you.
Chapter 15 good, bro.
What I have right now.
I don't know. What I was telling Austin is I like the general stuff about like family life and stuff like that.
Too bad you can't.
So to me, I like it more because I just think political
So it's
stuff.
not a very political.
Yeah, mine.
Yeah, it's just like family life.
Oh, no, I know it.
How they are treated and stuff like that.
Uh-huh. Some good some
I like
I don't do it.
It's like the class system too, a little bit.
Yeah.
Well, I did it with 4, so okay.
No, shut up. You see.
Okay.
I wish I
Who
could
has the better
make
grade here?
copies of
Who has
that
the A?
before I
Was it good?
That's debatable.
How is that irrelevant?
It's from the 50s.
I just got it at the local library.
I said on the test.
You meant just go to this extra
Long
here.
take
How do we
section
know
6
Austin's
exam, so I was like,
Wait,
That's
I
exactly why I did it. I was like, I had 4.
I probably would get 100.
Like, I'm there for 2 years. So that way my 4 is like 8.
I think you force myself to do it, maybe. I don't know if you really want that.
It's 16.
I don't think it'd be fun. No, I don't think it'd be fun, but I can sacrifice for a good grade. I think it's supposed to be fun. I think it's supposed to be more of a sacrificial.
I think it's what we fun for one part.
Yeah, I think it's supposed to be from the receiving.
We got it?
It's supposed to be from the
Yes.
receiver.
Okay.
what is it?
59 thirds is what I got.
I got 16.
Oh, I didn't do that right. Is that what you got?
I got 16.
I got 16.
Mine is
Does it subtract right?
Let's see.
One of the
I must have
four.
subtracted wrong.
4 on first and then.
Oh, that's one.
Because we missed it.
48.
Okay, so 1/3 out in front, leave that alone till the very end. Antiderivative here is what?
X cubed.
X cubed and,
X squared.
oh my goodness, 1 to 4.
No,
We love ones, right? 4 cubed is, I see I didn't teach you your power tables, but that's 64.
Minus 16.
4 squared is
Oh, that's
16.
what it is. I didn't subtract.
Now notice I should really be going like
Parentheses.
this. The etiquette here on how to use parentheses I think really does matter, so kind of try to follow the etiquette, okay? Stop yourself from mistakes. 1 cubed is,
Okay.
that's 0, so 1/3 of
48.
48 divided by 3 is 16, and these are all, what are we thinking of that? I haven't been real picky about units yet, because we're just starting. So what are the units on that?
Squared. It's average.
It's an area. No, it's an average.
I like what Allison, great. Is this an area or an average? It's an average. So is it square units or linear units?
Oh.
This is linear units. Even though it has an integral, you might think integral always means area, but remember, this is kind of where we computed an average value, so this is units. Okay? Now all those other ones so far were units squared. Alright, let's stop there.
Mr. McGee, on our final,
Am I going to cry?
how many of the applications are the